blue Shishin. Okay. He deserves the credit for his hard work. Neil is going to share some really cool stuff with us here in terms of extracting player tracking data from video using non-stationary cameras and a combination of computer vision techniques. He's been teasing it for a bit now on Twitter, if you've been following along. Neil is a sports analytics developer at ESPN. He's been with the company since 2016, and as a Columbus native, he got his bachelor's degree in computer science at Ohio State. Neil is a part of the sports analytics group at ESPN, where they produce statistical models such as BPI, FPI, and NBA Real Plus Minus, and work on player tracking data from the NFL, the NBA, and other leagues. And I read faster than I should have. There, oh. Is it in?
Did you have the presentation on your laptop?
You did. I think we did. It was on here.
Because I saw the videos work on your.
Okay.
So here,
Take that. Are there things you want to say while I get it loaded up?
Sure. Yeah. So this presentation, I come from the basketball world, but this presentation is a methodology that can be applied to any sport. So I tried to recreate as many of the visuals as I could using hockey video, but there will be some visuals with basketball in them as well. So, and there's a lot of information to cram in here, and I only have like 15 minutes, so I'm going to kind of just hit the high notes on it. But if you have any questions or any comments or anything, I'll have my contact information up here, so you can reach out to me.
Time to submit your question and answer in the question and answer box.
Do we just want to try plugging mine in with the HDMI cord and see if it shows up? Or if it figures it out? It's not plugged in. Yesterday, just before noon. Of course, it's the largest PowerPoint. It's doing something. Yeah, it's not working on any laptop. Okay, there we go. All right. Let's see. Okay, so. Okay, so we're going to go on the fly here. So basically what we want to do here is we are trying to parse out player tracking data from broadcast video. Like I said, this is sport agnostic, so we can do this with hockey. We can also do this with basketball. All right, let's get started. So why would we want to do this, or what are the current problems with player tracking methodologies? It's really expensive. We can't afford as fans or outsiders to get access to it, and the people who buy it don't have much incentive to give it to us because it costs a lot of money. And we can't go back in time with it. We can only get it for games that we are processing live in real time, and whatever the hardware setup is for that game is what we're going to get out of it. We can't go back and add in additional hardware to get more data to it. And on top of that, the process is not transparent. These are black boxes to us. We don't really know how they work. We just know that they do work, and we're not 100% sure how accurate they are. So here's the new methodology proposal. What we're going to do is we're going to use non-stationary camera feeds like broadcast video and some open source computer vision software libraries to create our own player tracking data. So I call this computer vision tracking, or CV tracking for short. We're going to create a new approach that is transparent so that the process can be reviewed and improved. And I want to create a blueprint so for anyone who's interested in doing this themselves, they can go out there and start making it on their own. So what are the inherent benefits to this? We can go back in time with this. We don't have any pressure to process the games live. We just need the video. We don't even need to be on the same continent as the game's being played in. We don't need to be in the facility. We don't need to have access to the rafters or anything like that. As well, this is something that only costs man hours, not tens of thousands of dollars. There are some parts of this that are going to require some human intervention, and with some more development, we can hope to minimize those. And on top of that, we don't need to stick devices on the players' uniforms or pads. I do think a sensor-based player tracking data set can give you the highest quality, but you have to make sure that they're wearing the right pads, that the batteries are charged, all that type of stuff. So you don't have to worry about that with this. So drawbacks and disclosures. CV tracking works on the assumption that the broadcast video shows enough of the game. I mean, when you think about it, the broadcast is showing the most important part. It's showing where the puck is, where the ball is. So it should be capturing the action that matters. But there will be times where players are off camera, and we're going to have to account for that. This talk also doesn't cover ball or puck tracking. That's going to have to require a completely different process. So we're just not going to talk about that right now. And there have been attempts to do this before. Obviously, the most notable one is SportLogic. They do it for hockey and soccer, as you guys well know. And as far as I know, they do a really good job. And on top of that, someone else has presented on this before in the past, but it honestly just seemed to be theoretical, while this is meant to be practical and reproducible. So what is the high-level approach to this? We're basically going to be creating 3 separate data sets and then merging them all together to create player tracking data. We're going to get player pose estimations, we're going to map out the quarter ice, and we're going to get game context. So the first part is parsing player information from the video. So what we're going to do is use 2 open source softwares called AlphaPose and PoseFlow. Those basically identify in an image or in a video exactly where the person is and where their body parts are. So that's where you can see the colored skeletons on all the people in the video. And PoseFlow basically takes a series of images or video and make sure that the person in that frame is the same person as in previous frames. That's a whole separate problem. So here's some of the technical stuff. So once we have that, we can apply that to hockey video. So that's where with this, I split the game video up into video segments where we're just having continuous shots of the action. And then what I do is I run AlphaPose on that, and then I run PoseFlow on top of the AlphaPose output, and then I visualize it to what you can see here. So it's a little small to see, but basically it's picking up as many people as it can. It's picking up the people on the ice, which is good. It's also picking up people in the crowd, which we don't need to worry about at this point, but that's where the first human intervention part is mapping the IDs that are above the people's head given to them by PoseFlow to IDs that we are giving them for our own information. So we know who they are, what team they're on, what number they're wearing, that type of stuff. So once you map that, you can filter things down so that you only have the poses of the players on the ice. And as you can kind of see it, but you can see the mapping between their ID given to them by PoseFlow and our ID, which is just a letter in the alphabet. So once we have that, we're going to calculate the center of mass, which is going to be that coordinate for the person in our player tracking data. Very simply, what I do is I just try to get or estimate the average position of their ankles in these poses. If we don't have the ankles in the pose, we can estimate that too. And that completes the first part of this process. So the next part is where we're going to want to parse out the core or ICE information from the video. To do that, or our approach to that is we want to know where specific parts of the court or ice are within the video, so we can take the coordinates of the court and the people in the video and transform that into our static coordinate system that we typically use for player tracking data. So that's where in the video we're going to look for those points where those letters are and use those to create the transformation function, because we know the measurements of the court or ice. So to do that, I use what's called OPENCV's template matching function, and very basically what it does is it takes a template image and tries to locate it within a source image. Where is its exact coordinates? So you can kind of see in the picture, it's kind of hard to see, but there's a red square indicating that the algorithm found the template image. So to make that work a little bit better, I do a little bit of pre-processing with the video frames. I basically try to emphasize features on the ice or the court to help it. And that's where, for this example, what I did was I got the face-off circle and the Big Ten logo and used those as template images. And then I basically I converted it to black and white so that the markings on the ice were much more distinct. And that's where you can see the algorithm takes the template images on the left, it applies it to the source image on the middle, and the result is it locating, as you can see with the green rectangles, the template images within the source image. So once you do that, you can run that for the entire video frame and then re-visualize it to make sure things are working. And then that's where you can see it's doing the green circles on those spots. So we know for those frames exactly where the ice is. So the next part is the easiest part. It's basically parsing out the game context. Basically, we just want to know, like, for each video frame, what period we're in, what the game clock is, and just very basic things like shot clock for basketball. So basically what we're doing is we're applying optical character recognition, or OCR, on the scoreboard that's on the screen. To do that, I use what's called PyTesseract. And it's just a very basic process. We're basically just cropping the image to the numbers we want to parse out, and then we want to kind of transform the output text into a serialized form for each video frame. Now, the next part is we want to merge everything together. And to do that, so this is for a basketball court, but we can obviously do this for hockey too. Basically, we have the coordinates for the players on the court in the video frame, and the video frame has the range of the video frame on the x-axis is 0 to 1280 pixels, and on the y-axis is from 0 to 720 pixels for a 720p video. Now we need to understand the coordinate system for the court, and for a basketball court, in this system, center court is 0, 0. The y-axis is from -25 to 25, and the x-axis is from -47 to 47. And that's because an NBA court is 94 feet by 50 feet, and 1 unit in this coordinate system just equals 1 square foot in real life. So how are we going to transform it? We are going to transform the coordinates using a series of affine transformations. Since we are working with 2 independent planes, we can simply create a function to convert a set of coordinates from one plane, the video plane, to another, the player tracking plane. We know the exact locations of the coordinates of the court features we have mapped in our player tracking coordinate system, but not the players. So we can use the known coordinates to create transformation functions for each court feature that is mapped, and then apply that to the player coordinates to get the location of the players in our player tracking coordinate system. So once you do that and you revisualize everything, you have your first version of player tracking data. But as you can see, it's kind of not perfect. It's kind of messy. It's disappearing for certain parts when players aren't on the court, and it's kind of jittering around. But that's okay. That's where we can work with what we have. So yeah, these are the issues I mentioned. It's just noisy. Coordinates are missing in certain spots, but that's okay. So what we're going to do is we're going to scrub things. The first thing we can do is solve all these problems automatically by applying some filters. A Kalman filter is going to smooth out the noise, so when you see a player moving across the court or ice and they're kind of jittering, the Kalman filter will make sure that's smooth. We can apply an educated guess between 2 known points for a player to fill in the missing gaps. So if we see them and then they disappear and then they come back, we can just create a simple linear function for the time that they're missing to go between those 2 points. And this is where human eye will also have to make sure that everything's looking good, making sure that nothing's super wonky. And if there's anything that needs to be manually corrected, this is the time to do that. So once you do that, you can take a deep breath, and you can see that the results are a lot better. So on the left was the previous animation. On the right is once we've applied all these steps. When the dots go a lighter color, which it might be a little bit hard to see, that is where we are applying an educated guess for where they are. And yeah, this is a great first step. And here's the source video. It'll take a second to load, but the source video that I created the data for is on the left, and the output of the player tracking data is on the right. Guess it's not going to load. So, all right, we'll move on. So that's where after this, I did some accuracy tests. You guys might not be as interested in this because it's for basketball, but basically the result of it I came out was that I probably had too small of a sample size for it. Asking people to volunteer their time to look at the diagrams of my player tracking data and then compare it to the league's provider and only have the video frame that it came from is very time intensive. So I thought 300 samples would be good enough, but it probably shows that it isn't, because it showed that my system was actually more accurate than the league provider system for the sample, and I don't think that's true at all. I think it shows that the league, all of these player tracking data providers, they're not going to have 100% accuracy. They're going to have near 100% accuracy, but not 100%. So at this point, that's where I ask you to check this out for yourself. This link will give you a zip file containing some raw player tracking data that I showed in this presentation. It'll give you the raw source video from which it came from. It'll give you the moving dot animation video, which would employ here, so you can look at it for yourself. And it'll give you some player mapping info so you know who's who. So I just want to keep the conversation going on this. I want you to look at it for yourself. I want you to decide for yourself how good it is or isn't. And there's a lot of next steps with this with which I want to improve. So here are just a couple of them. I basically want to help automatically identify the poses to the people only on the court or ice versus getting all the people in the crowd too. I want to identify where the ball or puck is. I actually have some good ideas on how to do that, but haven't had time to fully explore them. And I'd like to do a proper ghosting model to fill in those gaps instead of just kind of doing a linear time function between where they were and where they are now. And to utilize this pose estimation data, this is a whole new data set that has a bunch of untapped potential. So at this point, this is my contact information, and this is the link to the data again. If you have any questions, feel free to reach out to me today or to reach out to me online. And I thank you for your time.
Okay.